So in this video, we're going to look at the sine function, which is the first of the trigonometric functions that we are going to be investigating over this course. If we look at the basic sine curve, from what we learned earlier, we can remember that it is a repeated curve. So if we extend this further along the x-axis, we're just going to see that repeated peak and then trough shape. So I'll show you that now. So we've got our original curve, which goes from x equals 0 up to x equals 2 pi. And that's just going to repeat within that same period. So you can expect to see the same values in the y-axis just by adding 2 pi to that x value. So when x equals pi on 2, y is going to be equal to 1, which we can see here. And if we move along by 2 pi, we can see that when x equals 5 pi on 2, we again have y equal to 1. So just to reiterate, pi on 2 in the x will give us 1 in the y. Pi in the x will give us 0 because it's at the baseline. 3 pi on 2 in the x will give us -1, and 2 pi will give us 0 again. Notice that we have both degrees and radians in the x-axis. Most of the time we're going to see the radian measure used, but just so that we are aware, you may see degrees. The degrees has to have that degree symbol though. It has to have that, otherwise we're just talking about a different sort of transformed function, which we'll talk about in a second. So within the family of sine curve, we've got 4 different transformations that we're going to look at, and we refer to them as basically A, B, C, and D as the coefficients or the variables that affect that transformation. This is all exactly the same as what we did in our first topic of functions and graphs, where we were looking at vertical dilation, horizontal dilation, vertical translation, and horizontal translation. So on our left, we have got the basic sine curve. So just like we looked at before. So we can see that when it hits 2 pi, it repeats itself. When we're transforming using vertical dilation, so we're focusing on this a variable. Now, this is out the front of our sine of x. So basically what we know about any value that you put in front of the rest of it, it's going to affect how much it is stretched. So if we're talking about stretching a sine curve or shrinking it down, if it's a number greater than 1, such as 2, then that means it's going to be 2 times as big as it previously was. If it's half, it's going to be half as big as it previously was at each x value. So let's go through and look at what happens if we transform it using y equals 2 sine of x. So at pi on 2, usually it's 1, but we're going to go up to 2. When we get back down to pi, and the same as at the origin here, when we get to pi, it's 0, so we can't do anything there. If we times it by 2, it stays at 0. At 3 pi on 2, we were at -1. Now we're at -2. Again at 0. 1 goes to 2, 0 goes to 0, 2 goes to 2. Now, if you are wanting to get a more accurate drawing, which is not always really necessary when we're just showing that we understand the dilation, you could look at values that are, for example, here, and you could say, okay, that's 3 units, so let's double that to get 6 units. That's just going to give you a bit of a better curve when you start tracing it. So let's just trace that one out. It's probably not going to be super accurate, but you will get the picture. Now, the key thing here is that we need to make sure that we are meeting up at these pi, 2 pi, 3 pi, and 4 pi. That's the key part here. So again, if we're looking at our second one, which is half sine of x, when we just read through it, we see that y is equal to half of whatever sine of x is. And if we've got sine of x here as our reference point, that means that we're just going to half every value of the y for the same x coordinate. So at pi on 2, we had 1. If we halve that, we have a half. At 0, half of 0 is still 0. Half, 0, sorry, negative a half, 0, half, 0, negative a half, and 0. So again, we're just going to trace this as best we can without it looking too bad. When you're answering these questions, the key thing is just to try and get some kind of curve. I know it's a bit wobbly because I'm using the pen on the computer, but overall, that is the kind of effect we're looking for. Now, we can also talk a little bit about the amplitude of the graph, but basically we're using a new terminology, which is this little modulus operator here. So if there's two lines around the outside of that, we're basically just knocking off the negative if there is a negative there. So initially our amplitude of the regular sine function is just going to be 1. If we have y equals 2 sine of x, our amplitude is the modulus of a, which in this case is 2, so that's just 2. If, for example, we had y equals negative 2 sine of x, our graph would be reflected or flipped. The amplitude would still be 2 because we're basically just talking about what is the biggest distance from the maximum to the maximum to the baseline, or the minimum to the baseline. With our next transformation, we've got horizontal dilation. Now, horizontal dilation is effectively we are pushing that curve kind of like a spring. So we're either pushing it from the right-hand side so that it is repeating more often. So it's like a kind of double zigzag or even triple zigzag compared to the initial one, or we are stretching it out. So we might only get one period in comparison to these two periods that we have here. This is a tricky one because it's kind of counterintuitive. So let's look at y equals sine of 2x compared to our overall function definition, which is y equals sine bx. So b is equal to 2 here. Our scale factor is actually equal to 1 on b, which is going to give us 1 on 2. So if our scale factor is a half, that means that we are reducing this in the horizontal direction. So we're pushing it back, or effectively squeezing it towards our y-axis. So what that's going to do is we look at our y coordinates and we're basically going to be halving the amount of times that they're going to along our x-axis. So if our dilation is a half, then we know that we're going to get, within this first half of the period, we know that we're going to actually get our whole period again. So instead of there being that larger period that we had at the start, we have this. So if we think about it in terms of like oscillations or periods of that curve, we can see that by the time our blue line has done its first one, we've already had 2 of our pink one, which is the y equals sine 2x. Conversely, if we look at sine of half of x, our scale factor is going to be 1 on a half. Now, when we divide by a half, that actually doubles it. So our scale factor is 2. So if we look at what happens when our scale factor is 2, that means that when we actually, in our graph here, had 2 full periods of this blue regular sine function, we're actually going to we're going to find out that we only actually get one entire period here. So if we follow the green one, we are going to see that we're just getting the up to the maximum, back through, down to our minimum, and back. The key thing here is that our maximum and minimum do not change. The only thing that's changing is that we are either stretching it in the x direction or pushing it back or squeezing it in the x direction. So it's usually useful to think about the sine function a bit like a spring, just because generally that is what we are doing when we're dilating it. We're either stretching it or pushing it back into its original state. So after looking at those two different dilations, we're going to start looking at translation. Now, the actual act of translating is actually a bit easier in terms of how we draw it. It's just more about interpreting the form of our function. Now, it's something that a lot of people do get tricked with because the form of this function is sine of x take c within the brackets, really focusing on the fact that there is a minus sign here. Now, the c is referring to how much it is translating in the x direction towards the positive direction. So, for example, in our first one, we have y equals sine of x minus pi on 2. So that means that our c is equal to pi on 2. What that means is that we need to move our whole function to the right by pi on 2. So if we look at what's happening at 0, that is now going to move to pi on 2. If we look at what's happening at pi on 2, that's going to move across to pi because that's the same amount of movement. And then once you get to this point, you can basically just continue to imagine that it's shifting across by that amount. Now, we also need to think about what's happening on the left-hand side of the screen because we don't just start drawing it from this point here because there's a continuous function when we have sine. Sine is just continually going from negative infinity in the x direction to positive infinity in the x direction. Because we know what the sine function does, we can kind of figure out that we're just going to continue that one down to here. If we look at sine x plus pi on 4, now this is a bit trickier in two respects. First of all, because we've got this plus here, so that means that our c is equal to negative pi on 4. Because for that to become x plus pi on 4, it's the same as saying x minus 4, and you want to match that up to our form of the function up here. So if we're moving it backwards by pi on 4, now that's only going to be like half of these spaces that we've got drawn in on our graph on the left. So let's just start with a point that we can clearly see, which is going to be this maximum up here. So we need to move that back by half, which is effectively the same as the pi on 4 because our from 0 to here is pi on 2, so half of that is pi on 4. We look at our next one, we move that back. We look at the next one, we move that back, and so on and so forth. Generally, you will find the pattern pretty quickly, and we need to also remember that it is going to go back through here. So let's start off by drawing what we do know, not forgetting that we need to fill in that last blank on the left and right hand sides afterwards. Now, if we look at what's happening up here, we can see that it's going to continue to rise, but it's not necessarily going to go all the way through. It's kind of going to hit about here, and then the same is going to happen over here. Generally, you can follow your previous sine of x function there as well. Now, vertical translation is a little bit more straightforward in the way that we're looking at sine of x plus d. Now, remembering that the plus d is outside of what our sine function is here. So if we look back here, x takes c is within that function of sine. The plus d is just like adding a value in the y direction. So it's a little bit more straightforward to draw. If we think about what's happening, it's a vertical translation because we've started off with our sine curve and we're just adding or subtracting a value from it, which moves it up or down. So if I just said y equals 1, and then I said, okay, y equals 1 plus 1, then we're just moving it up. So that y value just continues to rise just by one single value. So looking at our first example, sine of x plus 1, we can see our scale on the left. So we're just going to move every point up by 1. Now, again, some of you might not need to draw all of that. You might just draw the first couple, and that's giving you enough to draw your full translation. There we go. And then if we've got sine of x minus 2, that just means we're moving it down by 2. So if we're at 0, that's going to go to negative 2. If we're at 1, it goes to negative 1, 0, negative 2, negative 1 goes to negative 3, and so on. So not too tricky with the vertical translation. It's probably the most logical one, as well as probably vertical dilation. It's just the tricky ones are going to be your horizontal dilation and your horizontal translation. Now, if we look at this monstrosity over here, you can see that we've got all of the members of the family of the transformations. So we've got something that is going to vertically dilate. We've got something that is going to horizontally dilate. We've got something that is going to horizontally translate. And then we've got something that is going to vertically translate. Generally, you're not going to get all 4 of those in a question. However, it is good to try and see if you can work through that. But if we look at our examples here, let's just break the first one down. So y is equal to 2 sine of x plus 1, which means we have a vertical dilation and a vertical translation. So the vertical dilation is going to stretch our graph by a factor of 2. So it's going to get basically double the size. But we also need to look at the vertical translation. So it's going to move up by 1 after we have done that doubling in size. So a good idea here is to imagine what it's going to look like if we double it in size. So I'm just going to trace this and then get rid of it, but it's going to look something like this. Very rough, but obviously you'd probably be able to get the picture. Then let's draw what it's really going to look like by shifting that whole thing up by 1. So that one moves up, that one moves up, that one moves up, that one moves up, 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 and up. We are going to get rid of that traced one, and we're going to draw a nice new twice as big and translated up by 1 graph. So that's a pretty tricky one because you have to kind of do 2 things at once. However, if you think about it in those 2 logical steps, then it actually comes out a little bit more straightforward. Now, our second one is going to be also the 2 very tricky parts, but let's think about it bit by bit. So the 2 here is going to be a horizontal dilation, which means that our scale factor is 1 on b. So if our b is 2, our scale factor is 1 on 2, which means that it's going to be a half. So we can imagine that it's going to be looking like double the period happening. And that's not that flash. Let's try that again. We're going to have double the period occurring within one regular period. The other thing that we need to notice is that we've got an x take c. So x take pi on 2 means that our c is equal to pi on 2. Now that means we're shifting it to the right by pi on 2. So if we look at what's happening here, and I'm going to draw this one in black just as our outline. So we've got our horizontally dilated. Now we're going to horizontally translate it. So this one is going to move across by pi on 2. So that's basically our new starting point. This maximum here is going to move across by pi on 2. This original one is going to move across. This one's going to move across. And we start seeing our pattern sort of come up again. And if we backtrack here, we can see that it's going across by every 2 little spots. Let's get rid of our little traced one. And let's draw it in. Now, the key thing to remember here is that not much is actually happening to that general curve shape. We're just pushing it in or stretching it out, whether it's horizontally or vertically, and we are just moving it across. So it's always going to have that repetitive cyclic nature. The only thing is going to change is how it looks afterwards.